So, hello everyone. It's a pleasure to welcome you directly from Rome. I'm in Rome, where Carlos is our technical support on that session. So please talk to Carlo if you have any technical issues. Just to warn you, this session is recorded, as you probably know, but just to make sure that this is clear. We have 7 talks. Each talk is, whether it's invited or contributed, each talk, the time slot for each talk is 20 minutes, but I will ask you to only speak for 15, or if you want to speak shorter, that's fine, but 15, and leave 5 minutes for discussion. I will warn you 3 minutes, I will warn you at 12 minutes, so 3 minutes before the end of the talk. And when you hit the end of the line, I will just say last statement or last will, as you will. But I will warn you when your time is up, okay? And 3 minutes before. So I'm sure, as all of you know, we had exciting news about the discovered black hole neutron stars. And as it happens, after several general talks about double black hole mergers, you know, by Bing, Zhang, Chris Fryer, and Marika Branchetti, we'll have several talks dedicated to black hole neutron stars and their potential detections, followed by some more general talks and even talks. We will be finishing with Tassos with a talk on double black holes and long GRBs. So that said, I would like to start the session, but before we go on, one more thing, we'll ask the questions after the talk is over, and let's don't even raise hands. It's a small meeting, it's very relaxed, so please just unmute yourself, put a camera on, and, you know, ask a question, and I will moderate, okay? And I will start a new talk whenever the questions are done. And for speakers, please turn on your camera. So we'll start the session with a talk by Bing Zhang on the selected topics about electromagnetic counterparts of gravitational waves. Bing, floor is yours. Please share your screen.
Okay, thank you, Chris. I didn't realize that it's 20 minutes. I thought it was 25 minutes, but I'll skip some.
You get 15, please.
Okay. All right, so thanks for the invitations. I'll talk about several selected topics. EM counterparts, we all know about GRBs and Kilonova, and this has been observed in GW700817. So I will not talk about these. So these are the selected topics. The first one is CCBC, Charged Compact Binary Coalescence. So these will make faint, brief FRB-like signals and relevant to plunging neutron star black hole mergers and even binary black hole mergers. The other one is the short GRB less long duration X-ray transits. So these are related to neutron star mergers, but with a long-lived remnant. And finally, if time allows, I'll briefly talk about the GW-GRB associated time delay. So all these topics are physically motivated, difficult to detect, and have profound implications. CCBC, so I got 2 papers discussing this, but the origin was the very first black hole merger, and we all heard about the putative this EM counterpart, short GRB, but later it was not confirmed. But in any case, there were a lot of discussions in the literature for different ideas, and my own scenario was charged black hole. I think Chris originally asked me to talk about black hole merger EM counterparts. I'm not a firm believer that these guys can make bright ones, but this is one possibility, which I will briefly talk about. It's an old paper, but the idea is very simple. If not only just black holes, including everything, if 2 objects that are merging, if one of them is charged, then according to Maxwell equations, it will make currents, and currents will make magnetic fields, and because the orbit is shrinking, the magnetic flux is changing with time, and it will induce more electric field, and then it will radiate electromagnetic radiation. So this is the statement I want to make. It's not a matter of whether CBC members are charged. It's a matter of how large the charge is and whether the signal is detectable. So this is the very general discussion. So for the each member, we can define a critical charge, which is defined by the mass of the member. So this critical charge is a very large number typically, because with this charge, the electric field actually will significantly change the space-time structure. But this Q hat is a dimensionless one, so the real charge divided by this critical one, and it could be a very small number. And the GW radiation is proportional to C⁵/G, the fundamental constant defining the luminosity. And it increased rapidly with the separation. When the separation is close to 1A, then this is roughly 1 order magnitude below this. But for electric field, for EM radiation, for electric dipole radiation, it's essentially also C⁵/G and with some A dependence, but now it is related to Q squared. Remember that Q is a dimensionless charge. So if Q is 10 to -10, this is 10 to -20. So very straightforward. And one can also work out the magnetic dipole radiation, again, related with Q squared. With a different A dependence, this is A to -15, the other one is A to -4. But the question is, can we have charged objects? And this is the formation of charged black holes by these authors in a nice numerical simulation. If the black hole is Schwarzschild, if the neutron star is non-spinning, after it collapses, it will make a Schwarzschild black hole. That's straightforward. However, if the neutron star is spinning, when it collapses, it will naturally make a Kerr-Newman black hole. It is spinning and carries some charge. And this is simulation results showing that Q does not go to 0. Of course, during the collapse, some charge is retained in the black hole. And the question is, how about after that? So it is still something need to be explored in detail. But at least for pulsars, for neutron stars, they are naturally charged because spinning magnets are charged. If you work out the detail, use Gauss's law, then a spinning neutron star with a, say, force-free magnetosphere will carry a charge. And if you plug in the Crab pulsar value, this dimensionless charge is 10 to -7. Okay, if we plug in the 10 to -7 to the formula I just described, it turns out that the luminosity could be up to 42 for electric dipole and 38 for magnetic dipole. And this is already in the range of FRBs. So, and the question is probably during the merger, because when we talk about the neutron star black hole mergers, especially for plunging events, which means there's no tidal disruption, no kilonova, no short GRB, this charged neutron star will be swallowed by the black hole. And something like this will happen. It is a very faint signal, but it could be related to FRB-like event. It may not be FRBs. If they produce FRBs, they can only produce a very small fraction of FRBs. So that was the first topic. The second topic is short GRB less X-ray counterparts. So we all talk about the tidal neutron star mergers, making a black hole, making a jet, making some kilonova, but at least some neutron star mergers will leave behind a magnetar, and there's rich phenomena associated with this, and one of them is the X-ray counterpart. So the idea is we are not looking down the jet, so it is short GRB less. However, the X-ray emission might be more isotropic. So at some other angles, we probably will see a long-lived X-ray counterpart associated with neutron star mergers. So again, this is the disclaimer. It's not a matter of whether neutron star mergers will make long-lived massive neutron stars. It's a matter of how often this will happen, because it depends on equation of state, depends on the masses of the two neutron stars. There are all different types of merger remnant. And this guy, which is the supermassive neutron star, living for hundreds of seconds, thousands of seconds, or a stable neutron star will eventually make a long-lived X-ray counterpart. Why we thought about this? Because in the GRB field, it's already some indirect evidence. For example, some X-ray flares following some short GRBs, or so-called extended emission following a short hard spike. And there are several papers already proposing some long-lived neutron stars. But the smoking gun to me was this so-called internal plateaus. Some short GRBs, actually a lot of them, about 1/3 of short GRBs, are followed with the X-ray plateau lasting for about 300 seconds. And then suddenly the X-ray plateau disappears. Appear to me this is just a neutron star collapsing into a black hole. And if we do the detailed studies, we find that the so-called extended emission and X-ray plateau is probably the same thing. If the X-ray plateau is bright and hard enough, it will show up as the extended emissions in some short GRBs. But all the bottom line is all these plateaus drop suddenly. The decay slope is too steep to be interpreted by any of the GRB afterglow model. It requires a long-lived central engine. And to us, this is just a long-lived neutron star magnetar collapsing into a black hole. Then the natural question is, for short GRBs, we see this short GRB and X-ray plateau. However, this is looking down into the jet. However, if we are looking in this direction, actually in most cases, we are looking not down into the jet, then we will miss the short GRB, but we'll still see this X-ray plateau. So this is why I proposed back in 2013, some short GRB less X-ray counterpart. And very interestingly, one of this candidate was discovered from the Chang'e Deep Field South XT2. This is the name of the source. And the light curve shows a almost flat X-ray light curve followed by T2 minus 2, essentially. So this is a test version of the magnetar spin down. And if you look at host galaxy properties, it is very consistent, all the aspects consistent with short GRBs. For example, there's a relatively large offset, and the fraction of light inside is large, which means it is in the outskirt of the galaxy. And the star formation rate is also pretty low. So everything is consistent with short GRB, except there's no short GRB. It's a long-lived X-ray counterpart. To me, this is a neutron star merger making a magnetar. So this paper was reported in Nature back in 2019. And very interestingly, recently there was another X-ray transient called 210423. And this one, I haven't seen the paper yet, but in ATEL, they said, okay, after its fast rise, it maintained a plateau lasting 4.1 kiloseconds. And the property of this one is very similar to the Chang'e Deep Field South one, XT2. So it's very interesting. We got two cases now, and my student Shenke and I worked on this source and studied the X-ray properties and all optical upper limits. It is consistent with having a neutron star merger because this guy is likely farther away than 1708 to 17. So bright kilonova is not expected, but for different parameters, it's quite consistent with all the upper limits. So we really hope to detect the true association in the future with LIGO and other GW detectors, and probably with a wide field angle X-ray telescope such as Einstein probe, and to see some joint simultaneous detection or with certain delay after the GW, we can see an X-ray counterpart rather than short GRB. Okay, so the third topic is the GW short GRB delay time. So this is related to 1708-17. So we all know this famous plot after the neutron star merger gravitational wave signal, and there was a short GRB, and the delay time scale is 1.7 seconds. And in this paper, minute review actually, I discussed several contributions to this delay time scale. So because everyone asked the same question, so what is the origin of 1.7 second delay? And somebody said, okay, the merger make some hypermassive neutron star and lasted for 1 second, 1 point some seconds, and then after the black hole is formed, the jet is launched. And somebody said this is related to fundamental physics, for example, propagation delay between EM and the gravitational waves, and some others. There are other ideas. So there's all kinds of possibilities to interpret 1.7 seconds delay. So if we ignore the possible physical reason, I think, for example, speed of light difference may not be that significant and may not be there at all. If we attribute this to astrophysical origins, then this delta T is composed of 3 components: delta T jet, delta T breakout, and delta T GRB. The first one, so this is a cartoon picture showing this thing. This neutron star merger will make a, so through merger or core collapse, I'm talking about long GRBs as well, will make a black hole torus system or a magnetar. So this is the first step. And then the jet is launched after a certain time. So this delta T jet is waiting time for the jet launching. And after the jet is launched, the jet needs to break out the ejector. It takes some time to get out of the ejector. And finally, after the jet gets out of the ejector, it will reach certain radius to produce the gamma ray burst. Of course, sometimes it will say after it gets out, then that's the GRB. But in the general GRB picture, it takes additional time to reach whatever GRB radiation radius. So we really talk about all 3 parameters here. And very interestingly, observationally, you can see that the delay time scale is about 1.7 seconds. If you measure the width of the burst itself, it's roughly also 2 seconds. And theoretically, actually the time it takes for the jet to reach a certain radius, the GRB radius, is this expression, and the duration is also this expression. So the coincidence between these two suggests that our delay time scale is probably defined by this guy. These two are not very important. So this is, to me, the delay time duration is not evidence for forming a black hole. So we do not need to say wait for 1 second or 1.7 seconds to make a black hole. The jet might be released right away, and then it just takes a while to reach the GRB emission radius. And in this table, I actually discussed all kinds of models for short GRBs or long GRBs. There are different types of jet mechanisms, or accretion, magnetic. So for different cases, what is delta T jet, delta T breakout, and delta T GRB, and the total delta T. The bottom line is for mergers, and typically this delay time scale range from, say, 10 milliseconds to 10 seconds. But for long GRBs, it takes at least 10 seconds, and sometimes could be up to 10,000 seconds. So in the future, if we see a long GRB associated with a gravitational wave burst, it will be very interesting to test the long GRB jet launching mechanism as well. Okay, so I spoke very fast. I don't know how I'm doing with time, but this is the summary.
You're doing very good. I made a mistake about time. You go ahead, please.
Okay, very good. Okay, so we have 3 selected topics to summarize. Charged CBCs. So many CBCs have been detected, and many FRBs have been detected. Most not from the CBC channel. However, we will reach the full all-sky monitoring and joint searches in the SK era. So implications, we can measure the charge of the CBC. So these guys, if they carry any charge, they probably will show up in a small fraction of FRBs. If we don't detect any, then in long term, we can really place a strong constraint on the charges of the CBC members. This short GRB less X-ray transients. So we already saw evidence in the afterglow short GRBs. We also detected 2 candidates. then we're really looking forward to detect the true associations in 0405 and this Einstein probe era. So implications, if we do see these guys, we know that they're making long-lived neutron stars, and we can constrain neutron star equation of states. And finally, GW-GRB associations with delay times. We have one case, but we expect to detect more in the future. And the implications is we can really unveil the jet launching physics. Okay, that's all. Thank you. I'll take questions.
Thank you very much, Bing. Any questions, please go ahead. I think Chris Fryer is raising his hand.
Yeah, so I have a question, Bing, on your having a neutron star remain in either a magnetar or a pulsar late time. And in GW 170817, at around 3 days, the optical is a little brighter than some of the Kilonova models predict. And my question is, you mentioned it briefly. Is there any way to explain a small bump in the optical at 3 days with some kind of strong pulsar in GW 170817?
Yeah, thanks, Chris. Yeah, so I know you guys have a paper. We also had a paper discussing more the same topic. So in the 170817 case, I think at least when we start to observe it, a magnetar is ruled out. So, but the possibility of having a long-lived low B field neutron star is not ruled out. Actually, it is quite helpful to, as you said, to explain the blue component at the peak time. So if we really just use the black hole launched Kilonova, I think the opacity does not work out because that blue component was too bright and too early. So if you take a standard, the opacity, say 1-ish, then if we make the Kilonova bright enough, it will be delayed. It cannot be that early. And if we make it early enough, it cannot be that bright. So a way to help out is to have a long-lived neutron star to inject energy. So I think the case for 170817 is not settled down. And the pity was we didn't really have the prompt X-ray observation, say within 1,000 seconds. There might be a, say, supermassive neutron star there. There was a plateau and it collapsed within some say, thousands of seconds. And that way you can actually increase the energy of the ejector somehow. Yeah, so it is an excellent question, and we really hope to see more cases in the future to find it out how common these guys are.
Very well. Any other questions to Bing? You can just unmute and speak up. Okay, Bing, in the meantime, I have a question. It seems like we'll be talking a lot about black hole neutron stars in near future. How can we use electromagnetic data on short GRBs to tell which short GRBs are coming from black hole neutron stars and which are coming from neutron stars? Can we already do that, or are there any prospects for that?
Excellent question. So that is even harder to do, but at least we can tell the other way around. So if we do see an X-ray, say, internal plateau, and some hard job after that, to me, those should be related to neutron star mergers. Whether those short GRB without this plateau are produced by neutron star merger or neutron star black hole merger, that is hard to tell, because if they make black hole immediately, then both systems probably behave similarly. It's not easy to tell.
I see. Thank you. And I see we have a question from Alessandro. Please go ahead.
I Bing. You were mentioning all these time scales, and it's very interesting. A few years ago, with Brian Metzger, we wrote a paper trying to answer essentially a similar question. I mean, the question is, why, in the case you use this proton magnetar model for the gamma ray burst, why the duration of short gamma ray burst is so short, no, and the long are so long. And essentially, our answer was that in the case of the short gamma ray burst, the real duration, the intrinsic duration of the burst is related to, in our scheme, of course, is related to the time of the confinement of the quarks. Essentially, it is very short because the moment in which you completely deconfine your neutron star, you switch off completely the production of hadrons from the surface. And in the protomagnetar model, that implies that you stop essentially having a jet with the proper Lorentz factor. So I would like very much to discuss with you about this duration, because I think that they play quite an important role also in the scheme that we developed with Brian Metzger. So I really would like to discuss with you about that.
Yeah, thank you, Alexander, for the comments. Yes, I know your paper. Yes, so if the short GRBs are powered by black hole accretion, then the short duration is easy to understand. If it is powered by a long-lived object, then we need to come up with another time scale to make a short duration. And your proposal is definitely a very good one. And another possibility is the differential rotation of the neutron star during the differential rotation phase, and probably some magnetic activities can power relatively short duration burst. Regarding the quark star remnant, actually, we had another paper with An Li. So if we want to interpret the cutoff of the plateau as the collapse of the neutron star or quark star, then different equational state have the different distributions of that collapsing time. Observationally, that collapsing time distribution is very narrow. It's about 300 seconds. For most of neutron star equational state, the collapsing time is spread in a much wider range. But for quark stars, it actually does better. Yeah, so that is from another angle. Probably, I'm not saying that is a proof, but it could be another evidence of such kind of scenario.
Okay, Bing, thank you very much for answering questions. I think we'll move to another talk, but before we do, I need to apologize. I made a mistake. Bing was right. Talks are 20 minutes plus 5 on questions. And Bing, I let you speak, but sorry to make you rush. Okay.
But it worked for me at least.
Thank you so much. So we
All right.
switch to Chris Fryer. Chris, you have full 20 minutes. I will give you a warning sign before 3 minutes before the end. Please go ahead.
Okay, can you see my screen?
Yes, you can make, yes.
Great. Okay, so I'm going to talk about some of the uncertainties in modeling kilonova emission. And let me start with why do we care? Because there's been a lot of there's been a lot of discussion on kilonova and how can you match them, and we discussed this a little bit with Bing's talk on can there be a pulsar, long-lived pulsar in GW 170817. What was great about GW 170817 is it really did tell us that you do produce ejecta from neutron star mergers. You can get a jet out of it. So the wealth of data really told us a lot of information. These produce GRBs, they produce ejecta, but the amount of ejecta and the composition of that ejecta was a lot harder than I think the community realized to pin down. And Benoit Cote did a summary of all the papers and their estimate, well, not all the papers, a subset of the papers and their estimates for the mass ejected, both, in this paper, he threw it into 2 different components: dynamical mass, which is low IE ejecta, so low electron fraction, so it's all about heavy R process, versus a wind ejecta that maybe is not so low electron fraction, so it has materials that is more like the first peak R process or even iron peak elements. So he divided it into those 2 distinctions. The dynamical ejecta is what you really need a lot of to explain the R process elements. And the amount that was predicted depended on the paper. And I would say depended on the group, but it turns out it actually depended on, there was some of these papers listed here are the same modelers, but they're looking at different data, or they tweaked their models over the course of less than a year, right? This all happened. These are papers coming out in 2017. But the range of dynamical ejecta went from almost 0.001 solar masses to 0.04. And oftentimes I hear in the community, they say, oh yeah, we know it made 0.04 solar masses of our process elements. That is not, we cannot prove that based on our models right now. It could be 40 times lower than that. So that's the thing to bear in mind. Depending on the models, you got a different result. And I want to go into why a little bit what those uncertainties were, but let me tell you why you should care. Why you should care is that if you looked at the neutron star merger rate predicted from GW170817, and this is another plot from Benoit Cote, and you looked at the amount that galactic chemical evolution needs to explain the R process, it was smacking, and you take either the high or, a value that's either high, and in this case, Benoit was looking at the European production. You can take something that's either 1.5 times 10 to the minus 5 solar masses, which is closer to that 0.04 total R process ejecta, or something that's 3 times 10 to the minus 6 solar masses, so something that's 5 times lower. You can explain with the rate that was given from GW170817, you can explain the R process elements observed in the galaxy. So you can use galactic chemical evolution and say it's all good. Now remember, when we looked at GW170817, its rate was a little high compared to the population synthesis models. And so at that time, it was like, okay, well, population synthesis models have quite a bit of uncertainties. If you look at those full uncertainties, you can still explain there is some overlap with the rate. One thing to bear in mind is after the science run, 03 science run, the rate for neutron star mergers has gone down by about a factor of 3. So if you look at Abbott et al. 2021, the rate is more like 80 to 800 neutron star mergers per gigaparsec cube per year. So that lowers it, and the nice feature there is that's in a lot better agreement with the population synthesis models. But now we're in a situation where if we produce at the lower end, if GW170817 is characteristic of neutron star mergers, and the production of heavy elements was at the lower end, we're no longer explaining that much of the R process elements with neutron star mergers. So getting the exact composition to better than this factor of 40 that we have uncertainties in our models is something we will need to do in the end to try to understand our process production in the universe. So let me tell you the problem with this trying to get detailed yields is that there are lots of pieces of physics and numerical science that go into producing what will the light curves look like. And so I just wanted this slide is essentially to go over some of those uncertainties for you. So you have the merger calculations, people like Radice et al. You have disk calculations, people like Miller et al. And those are the pictures I'm showing. But there's been quite a few calculations where they're trying to calculate doing the best calculations they can do. So there's numerical artifacts in the angular momentum conservation. There's different levels of how well do you do the neutrino physics. There's equation of state effects. And then there's the fact that none of us can run these models long enough that we're actually getting the final escape fractions from this ejecta. So when even these calculations that run out to a second, the ejecta from these winds are still accelerating. So we don't know what's escaping and what's going to fall back. We don't have that fallback fraction. In the supernova field, we've done this, but we can run the calculations to late times. And that's what we've been doing. And there's lots of arguments on fallback in supernova, but we're getting a better and better understanding of it in supernova. This is a much harder problem. And I think we're just hitting the tip of the iceberg on whether, what the total amount of ejecta is coming from the simulations and exactly what their ejecta trajectories look like. So the problem with this is that if you then take these trajectories that we don't understand well and put them into your nuclear physics calculations and do our process nuclear synthesis, you have both all the uncertainties in those trajectories, but now I'm adding on top of it all the uncertainties in nucleosynthesis. So there's lots of things like fission recycling, isomers can alter the yields. So there's a whole bunch of, then even after I've done these calculations, a whole bunch of additional physics uncertainties in determining exactly what the yields are like. And so there's quite a few papers. I put up one by Trevor Sprouse, where they vary different nuclear physics aspects, and they're getting very different yields. So that's another uncertainty. Then you take this material and you put it into the light curve calculations. And so they're taking all the uncertainties we have in the trajectory. What's the morphology? What's the velocity distribution of the mass? They're tying it in with all the composition uncertainties, which affect both the opacities and the energy deposition. And then they have to put in numerical models, which have the inclusion of the atomic physics uncertainties and how you implement that atomic physics. So on the bottom right corner, I have a image by Oleg Kuropkin where he was trying to study what are the, no, this is actually by Ryan Walliger, where he's studying the yields and the variations in the light curves by playing around with a lot of these free parameters. So we have a whole set of uncertainties that we have to understand if we're going to understand what are the true ejecta from these mergers. So let me just I'm going to just touch on a few of these uncertainties in more detail and describe kind of where we're going on trying to answer these questions. One of the ones that Jennifer Barnes has studied a lot, her first paper was in 2016, but she continues to publish and study aspects of it, is how do you, when you have this ejecta, the interesting thing about neutron star mergers is you have a wide range of radioactive isotopes that you're considering, and as they decay, they deposit energy from gamma rays, from electrons, from alpha particles, from even big fission fragments, trying to see how much energy do these objects, when they decay, how much energy do they deposit into the ejecta. Understand that this is not a trivial calculation. What Jennifer has been doing is increasingly sophisticated models, but they still assume things like angle averaged interactions. So you'll see in her recent papers where she talks about stopping power, that has a lot of assumptions made into it in how well do these, the fission fragments, the alpha particles, the electrons deposit their energy. Getting that answer right will change your light curve. So if, as she modifies her calculations, she gets different answers. And when she was looking at some observations by Wen-Fei Fang, she actually played with the energy deposition parameters because it's not fully understood to try to match the light curves, especially at 1, 2, 3 days. So there's uncertainty just getting that deposition right, which we don't do very well. It's a simpler problem with supernova, but even with core cloud supernova, where you're only worried about nickel 56, there is a lot of work that you have to do to try to get the right energetics, energy deposition from these radioactive decay. So this is just one of the free parameters or one of the uncertainties we have in doing the light curves. Another uncertainty is the morphology. So Oleg Kuropkin played around with these bizarre morphologies where he played with a 2-component model. So he has 2 components. Each component has a single composition, and he just varied those parameters. This is not even coming close to varying the parameters of the ejecta the way nature is actually producing it. Actually, nature has a variety, a composition that varies with velocity, that varies with angle, a mass ejecta from the mergers that varies with velocity and angle. And you have to get all of that done correctly, and actually time. It also varies with time. You have to do that all correctly to get the right light curve. But Oleg just varied a morphology, 2-component model, so two compositions, and asked the question, how does that change the light curves? And in this plot here, I show how much it varies the light curves. So these are models with the same total dynamical mass ejecta, but he varied the morphology. And you can see that for several magnitudes in the K-band and G-band light curves, he gets very different answers just by varying the morphology. So there's I can match, with the same ejecta mass, I could match quite a few different light curves just by varying the distribution of the ejecta. I can tell you that if I started to do the full uncertainties in the ejecta properties, I could match almost any of, I can match a wide range of light curves even with the same total mass. And so the other way to say that is I get a light curve and it can vary with quite a range of masses. I can still match the light curves unless the data is really, really pristine and we get lots of data. So there's a big need to get better and better data to try to constrain these ejecta models. For the final kind of example that I wanted to give, I wanted to talk about some of the uncertainties in the opacities. This is one that we argued about a lot. It's not just calculating the opacities, doing the atomic physics right, but it's in how do you implement it into your code. And funnily enough, the astronomy community seems to be happy with this kind of expansion opacity formalism that both Phil Pinto and Ron Eastman came up to model type 1a supernova. What this is accounting for is the fact that as you have a photon leaving the system, the lines that the photon will see get broadened by the velocity gradient in the material. So a photon, even though its energy is not exactly aligned with the line, will still hit these lines. But then they also are correcting for the fact that as the photon moves, it can get out of the lines as well. So it's more likely to hit a line, but it's also more likely to get out of the line. And when you have lots of lines in your system, this is something you need to correct for. And Ron Eastman and Phil Pinto developed a formalism that we use for type 1a supernova, and it seems to work fairly well. But the question is, they did have to tune it to get the right answer. And the question is, did the tunings that they made to match 1As, are they right? Or did they just, because they knew what answer they wanted to get, did they get a fit and then tune it to fit it? So it isn't, I would call it an engineered solution. It's not full physics. There was a knob that they tuned to try to get the right answer. And we can talk about that in detail if anybody wants to. Or is it, and then if you've tuned it for 1As, is it appropriate for Kilonova? And so at some point, Chris Fonts led an effort where they used the best data they could from the atomic physics, but then calculated a few different ways of doing the calculations, one using a pure Sobolev approximation, one using this kind of expansion approximation, and one just doing bin opacities. And what you see is the expansion approximation for Kilonova and the bin opacity method actually get very close to the same spectra for an answer, but a pure Sobolev solution gets a different one. So, but they're all fairly accurate. So I think we're feeling better about the opacities, but there still are some disagreements between the groups, and we're working on that now. So the approach that we're going to have to do to really do this model right is we're going to have to go across quite a few different fields of physics, dense nuclear matter, neutrino physics, nuclear cross-section, things like fission recycling, and atomic physics and charged particle transport and plasma effects, and then put it into codes that have the numerics and implement them into the codes that have the numerical artifacts as well. So there's a broad range of fields that you have to study just to get a Kilonova light curve and actually go from, I have this observation, this was how much of some mass that we produced. And the good news is that NSF, NASA, DOE, what?
3 minutes.
No problem. So there's a lot of the NASA, NSF, DOE all realize that we need this kind of working together over a broad set of physics fields. And you'll see that there's a lot of centers being formed to help facilitate this kind of collaboration. There's an N3AS center, NP3M. These are different nuclear physics fields trying to work together with computational scientists to solve these problems. There's a CNAM proposal that's more doing nuclear cross-section that has also been proposed. So you'll see the reason these collaborations need to happen and these centers need to be produced is we need to somehow break the boundaries between different fields of study and work together to solve this problem. And I'll just say, the other thing we need to do is realize that there's more observations to help us than just, I got a gravitational wave event and I'm going to use that to constrain, I'm going to get some electromagnetic radiation from that gravitational wave event, and I'm going to get some data. And one of the ones that I would say that I think will be very useful is studying the, tying to nuclear physics, looking at the detailed nuclear physics yields with fields like gamma ray astronomy. So I just wanted to give a plug for, there is a reason why we need to look beyond just hoping that we'll get this all from these kilonova light curves. We're going to have to look at different observations, and gamma ray astronomy is just one example. And with that, I'll end my talk and take any questions.
Chris, thank you very much for your talk. And any questions to Chris? Please just unmute and speak if you have a question. Chris, if you're waiting for questions, let me ask one about heavy elements. If let's say LIGO rate for double neutron stars will still go down after 04, what would be your top contender or contenders to produce heavy elements if it's not double neutron stars? What would you bet on?
So the problem we have, and we have the problem, people don't realize it, it's also a problem in neutron star mergers, is the observations look like the yields have, there's maybe the first peak hour process has some, it varies between the ratio between first or peak hour process and the second and third peak hour process. There's some variation, but it looks like there's a fairly solid, the R process elements produced in the second and third, it's always the same ratio. You're always making the same amounts of those. The ratio of second to third R process peaks look very similar. And the reason we don't like supernova as a production site is it's hard to imagine how supernova can make such a non-varying distribution of R process elements. But we have that same problem when you talk about disk winds from neutron star mergers as well. It's hard to explain the uniformity in the observations right now. And I at every talk I give, I tell the observers, how sure are you of the uniformity of the observations? But I think if you don't worry so much about that uniformity, then I think supernova, anything that forms these neutron stars will still be a viable candidate. And I think we'll be looking at things like, how can supernova produce, how much R process can supernova produce, and can we improve the yields from neutron stars formed in supernova and try and produce this R process. So I think I would not rule out supernova as a site for R process, despite the fact that neutron star mergers have some nice properties in them to explaining a large fraction of them. So I think we're still in the area where supernova need to be studied in more detail so we can determine whether they can make the R process or some of the R process. And I think there's a growing belief that they do make at least a portion of the R process. The question is, can they make a sizable amount with the uniformity we see in the observations?
Okay, thank you. I think you have Tassos with another question.
Yeah, so that's a short question. You mentioned that in the simulations that people are doing, usually you run it only for a second of physical time, and you are still in the phase where the ejecta are being accelerated. The numbers that are quoted are as ejecta. Is it the unbound material, which means that if you let them run for faster, maybe some more material will become ejecta? Should we treat it as a conservative limit, or it's the other way around? Anything that kind of moves outside is ejecta, so we should treat it as a optimistic limit.
Yeah, and you say that was a quick question. I think we need to look paper to paper. So what we started looking this with the work that Jonah Miller did, and it turns out he was doing everything that went across the boundary. And so he had an upper boundary, he just said any of that ejecta. And a lot of that ejecta is not unbound at the time that he finished the calculation. So in his case, at least, I think he gave an upper limit on the ejecta from his first paper. And but there may be others that actually only looked at the unbound material, only that material that was going higher than the escape velocity. So I need to, we just realized that, I just realized, I should say, that they weren't running, it wasn't like supernova where we run it out, we actually map things in and running out late enough that we can figure out how much fallback we have. They have not, I just realized they need to be worried about that. I need to go look at the papers and see exactly what they did. But I know at least with the Miller et al. Paper 2019, that's probably an upper limit on the ejecta. Some of that material will fall back.
Thank you.
Thank you. We have another question from Amadeo.
Yeah, so just to understand, let me see if I understood your point. So basically you said that to calibrate the supernova models, there was a kind of bias because we were already expecting something. And so for our models based on the observations are kind of biased. And after that you said, okay, so we must implement our models with what we know about how atoms and molecules behave. So my question is, but even in these regards, wouldn't there be a need for base our models on empirical data? Probably you cannot really hear me correctly. Let me see if just tell me if you heard me correctly, or if you heard me.
Yeah, and so I did hear you. And you're talking about do we need to help we have these models, and you can almost any of this physics you can pick and say, I have this nuclear physics models, and do I need to help calibrate them on empirical data? And the question is, across the board, yes. Like almost any piece of this physics, like for nuclear cross sections, one of the goals of the Facility for Rare Isotope Beams that's being built at Michigan State University is to help calibrate a lot of the physics in these from rapid neutron capture. And it'll take a while to calibrate it completely, but the way we're going to beat down some of these uncertainties is by doing experiments that will constrain them. And the thing to bear in mind is that experiments are going to be both laboratory experiments like the Facility for Rare Isotope Beams. For radiation transport, we actually do experiments here at Los Alamos where we're testing our radiation transport codes. But we'll also use astrophysical events to help calibrate what we're doing. So it's this weird thing that we're using all of this data to help calibrate our models, but at the same time, we would like to learn, once we understand the physics, we want to learn something about neutron star mergers. And so it's one of these things that works in tandem. And I think it's not going to be this sudden thing where we learn everything in one go. We're going to slowly increase our information, and we're going to do more and more experiments to help beat down the physics. So there's experiments to study the atomic physics as well. So we keep on improving both in laboratory experiments and better understanding from astrophysical events to improve this physics. And I think that will help the models. Does that answer your question?
Yeah, so just to see if I understood completely. So the point is that if we make more experiments, we get more knowledge, and we can compensate for some intrinsic biases in building these models. This is what you are saying, basically.
Exactly, and so this is something that it's a major effort across a lot of disciplines that we're working on. So this is I'll go back to the fact that I was talking about these centers that are forming in the U.S. It's the National Science Foundation, it's NASA, it's Department of Energy, and their whole goal is how can we help understand this physics better so we can do problems like this. And in fact, a lot of them our end problem is to understand neutron star mergers, but the physics we have to study, that's where we're doing a lot of experiments to try to constrain that physics so we can make better models.
Very good, Chris. Thank you for answering all the questions. Let's move on. The next talk will have Marika Brancesi, and she will tell us about multi-messenger observations with the next generation of gravitational wave instruments like Einstein telescope. Marika, 20 minutes, please.
Okay, can you hear me?
Yes, we can hear you.
Okay, perfect. So thank you for inviting me here. And so I will talk about the future. And in particular, I will focus mainly on the Einstein telescope. And so this is the interferometers that are looking at the sky now. And so from the next year, we will have an upgrade of these interferometers. And we expect that they will start observation after June 2022. There are plans for the future for these instruments. And in particular, there is the so-called phase plus for these instruments. And after 2025, we expect also LIGO India. And the scenario about neutron star and black hole changed a lot in a few years of observation of LIGO and Virgo, and recently also with CAGRA. So last year was not very sensitive, but we expect larger sensitivity in the future. This is the summary of what is multi-messenger astronomy with gravitational waves. So far, we detected only one event with a firm electromagnetic counterpart in all the band, a lot of observation, a lot of richness of data. And in particular, these events let us learn more about relativistic jet, kilonova nucleosynthesis. Also, we started to constrain in a better way the equation of state of neutron star, and also show us that there is a possibility to make also cosmology with gravitational wave, in particular for LIGO and Virgo, only estimate of the Hubble constant with large errors so far, but increasing the joint detection. So this is a really new way to make cosmology. But it will require time because we need to accumulate joint detection, and so far we have only this one. And I think that for cosmology, really the step forward will be with the next generation of detector. And in particular, also we know better about how compact objects form and evolve. And so what is the future? Let me start with the Einstein telescope and telling you one important news that we had this week. So after working a lot for the ESFRI, so the European Infrastructure Roadmap last year, since 2 years more or less. So 1 week ago, we knew that Einstein telescope was inserted in the ESFRI roadmap, so the European big infrastructure. This means that this is a starting point. So now all the funding agencies needed to find money, but this is the step really to start this dream. And so we are really very happy because this happened. And the Einstein telescope is a triangular shape interferometers. It's in particular a triangular shape, but is 6 interferometers, 3 at low frequency and 3 high frequency, is cryogenic, and you have, with respect to LIGO and Virgo, an increase in the power of the laser. So this implies a significant improvement in sensitivity, but also that we can broaden the frequency band going to lower frequency. This instrument is able to work alone, but it works better clearly if it is in a network of 3G detectors. This is the United States concept that is called the Cosmic Explorer. This is an L-shaped detector of 40 kilometers. So they are a bit different. Cosmic Explorer can be much better, in the high frequency band, but Cosmic Explorer is not the low frequency band that it will reach. So these are the sensitivity curves of the current detector, and in particular the phase plus of the current detector. And here you can see Einstein telescope, and in green Cosmic Explorer. This is Cosmic Explorer phase 1. Cosmic Explorer phase 2 will be better in this frequency band. So a factor 10 better sensitivity and wide frequency. And so what this means, the higher sensitivity means that we really can detect signal from all the observable universe. So for binary black hole, we can really reach the dark ages. We can make population study, and we increase a lot the number of detection. And in particular, you can see here from some population synthesis called the prediction of binary neutron star population and binary black hole population. You can see how much ET will be able to detect. And in particular, you can see that for binary black hole, and these are the binary black hole that we are observing so far. So using the mass distribution of binary black hole that we are observing now with LIGO and Virgo, what we can see is that we can detect almost the entire population. But also in the case of neutron star, if you look at the absolute number, they are really big. So we can have in both cases 10 to the 5 detection per year. So really this means that we can go to population study. And another very important thing is that for signals that are more close, we can really do what is called precise gravitational wave astronomy. So for the first time, we can have really a better parameter estimation. And this is crucial, for example, for equation of state, for all the, also to evaluate the distance of the object. And in particular, for example, for the merger of two neutron stars, we are really in a situation in which we can detect the post-merger signal that is extremely important to know what object formed there, because it's related also to the electromagnetic emission. And really going to lower frequency means that we can detect objects up to binary black hole, up to high redshift, also very massive black holes. So also in the range 10 to the 2, 10 to the 4. So we really are able to detect object, and I think this will be extremely important in connection with LISA, because it can show us what is the scenario, for example, of forming more massive black hole. And here you can see that the redshift is incredibly high. And I think that this is very important, for example, for primordial black hole. We expect an increase of primordial black hole at a higher redshift. So if we are able to detect a binary black hole at a redshift higher than 30, we can be almost sure that this doesn't come from POP3 star. So it's really very important to study astrophysical, but also primordial black hole. And for what concerns the sky localization, the fact that we have the low frequency in ET is extremely important, because we can use the movement of the Earth. And so in some sense, also if it is alone, is able to localize a number that is not negligible of binary neutron star merger. And in particular, we can have about 100 detection of binary neutron star with the sky localization less than 20 square degrees. So ET will be very important for astrophysics and also for fundamental physics and cosmology, so nature of compact object, the test of GR. And so I think that we can make a talk on each of these points, but I go ahead and go to the more multi-messenger side. So here is what you see before. So we can really go to high redshift. So we can make study of binary neutron star black hole along the cosmic history. We have a large increase of the detection rate, and we can improve a lot the parameter estimation. So all the things related to the multi-messenger, so Kilonova, equation of state constraint, nucleosynthesis, and GRB physics can improve with the Einstein telescope and the electromagnetic observatories, and also cosmology. And I will give you some number. So how we can estimate the joint detection. So for the first thing is to estimate the ET detection efficiency, and this for all orientation of the binary system, but also angle dependent. And so this is what I showed you before. The sky localization is important for multi-messenger study. And I told you that 100 binary neutron star per year can have a sky localization less than 20 square degrees. If there is also cosmic explorer, clearly the number of well-localized events will increase a lot to thousands per year. If IT will work with the second generation of detector, and in particular this simulation use what we expect for 5, you increase clearly the number of well-localized events, more or less of a factor 4, and in particular you can increase the distance up to which you can have well-localized events. That is important. So now, what are we talk a lot about the electromagnetic counterpart related to the gravitational wave signal, binary neutron star and neutron star black hole, so GRB and Kilonova. And you see what are the prospect of joint detection. So first of all, the sky localization will be good, but not good as arc-second. And so also in the future, we expect that the first phase of the search will be done by wide field telescope. Only if there will be 3 third generation detector, the situation can change and we can go to degree sky localization, or also a bit less than degree sky localization. So, and taking into account that the Kilonova emission is not extremely bright, what happens is that we will have 2 volumes of the universe. So we will be able to detect the Kilonova emission typically up to 0.3, also with the best instruments that we have now. And if you want to have, for example, the spectra like the one that we take with the ESO BLT shooter for the Kilonova, through which we are able to make nucleosynthesis, with instruments like ELT in the future, the redshift to have the same resolution is more or less at 0.3, 0.4 as redshift. So to go to higher redshift, we really need to have a counterpart. We need to use the high energy. So we really need to have a counterpart that we detect as gamma ray burst, and then a monitor that is able also to give the sky localization, and so that to drive all the follow-up. And I give you some numbers about Kilonova emission. So because the number then make also understand what is the step forward with respect to now. And in particular, we made some simulation with the Vera Rubin Observatory. The Vera Rubin Observatory in survey mode is not the perfect way to detect Kilonova. So in this work, we use target of opportunity with specific strategy to detect Kilonova with respect to other transients. And so this means that you need to ask time to the Vera Rubin Observatory. And in particular, we consider 3 epochs of 600 second observation in the 2 filter, so that you can use also the color. And what we found is that you can have joint detection around 60. Obviously, this I give you number, but this number have also big error that come also from, in this case, also from the error that you have in the absolute number of the population synthesis. But to give an order of idea of the number that we have in front, and ET plus the second generation, you can have 170, so around 200 detection per year, and asking to the Vera Rubin around 10% of the time of the Vera Rubin Observatory. Now it's impossible, clearly, because the Vera Rubin has some specific goal to reach, but in 10 years from now, in 15 years from now, this is not impossible, because they will have a higher amount of time for target of opportunity. And clearly, so we can really talk about Hubble constant measurements with really a precision that is the precision that we have now, and also better than the precision that we have now with supernovae or CMB. And for the characterization phase, for us will be extremely important to have a redshift. And for this, we can benefit of many surveys that will be in the next years for example, following Euclid or following the large-scale structure survey, in which people need redshift, and so there will be a lot of campaign with the different instruments like WAVES, DESI, MC. So all of these, I think, will give us many redshift that will be extremely useful to have redshift for the galaxies where we will have joint detection. And so this is extremely important for cosmology. The most expensive time at the telescope will be clearly for spectra, and so to characterize really the object. But we can expect that different instruments like TMT, James Webb Telescope, but also ELT can detect many transient, and that this one can be completely characterized. And so I think that also in this sense, the future is very promising, and that we can detect this object up to, as I told before, 0.3, 0.4 as redshift. So the high energy, also in this case, we did some simulation. The high energy is extremely important for the GRB part, so to understand better the jet physics, the GRB emission, but also to make cosmology in the sense not only the Hubble constant, but to estimate also the other cosmological parameters, and in particular also to make the test of modified gravity. And for GRB, we know that there are GRB, we know that we are able to detect GRB, and there are a small number of contaminants, so the time coincidence is the important thing to have the joint detection. And in the future, we have some promising concept, and to have, first of all, also softer X-ray instruments that can be really important also to increase the number of high energy detection, and also instruments that are able to make the sky localization.
Marika, 3 minutes.
Yes, so this is a concept in Europe. Unfortunately, ESA didn't select it 1 month ago, this mission for which we worked a lot also. And this mission is Theseus. I describe this because I think it's something that we need for the future. And this instrument has a broad field of view and a very broad coverage from 0.3 keV to MeV, and has also an infrared telescope. And with the Theseus, we made estimate of joint detection using the detection efficiency of ET, and also taking into account the structured jet that we observed for GV170817, and so the capability of Theseus also to detect different energy, this structured jet. And we came out with very conservative estimate. We arrived to about 10 detection per year with an instrument like Theseus that is able to localize. This is the important thing, that Theseus then can drive the following follow-up. This number can increase if we include not only the prompt emission of a structured jet, but if we consider all the structure that we are now observe in GRB, like the extended emission, like the plateau, and possibly if there is, so far it was not detected, but if there is an emission in X-ray powered by the spin down of a newborn neutron star. And so taking into account also of this type of emission, it's possible to increase the detection also to 100 per year. I give you also, this is a table that summarizes preliminary results on joint detection also with our other instruments. Here you can see that there are some instruments that are pretty old, and for us it's extremely important to think to future detector, because if we want to detect counterpart for the third generation of detector at the high redshift, it's extremely important to have high energy instrument online. And so this means that if we want to reach a high redshift, as I already told, the high energy is extremely important. And I want to show you also another thing that is very interesting. It's only one slide. So we really can test also with one event or few events, also modified gravity, because there could be a different propagation, gravitational wave propagation. And so we can have a different luminosity distance with respect gravitational wave distance. And there are models that predict a big difference if you are able to go to high redshift. And this is my last slide that summarizes the plethora of instruments that we expect in the future years that can help the Einstein telescope or that can work together with the Einstein telescope.
Marika, thank you very much for this enlightening talk on all those future instruments. Let's see if there are any questions. I have some, but Tassos is first.
Hey, Marika, thank you for the talk and congratulations for getting ET into the European infrastructure. You did a lot of work, I know. So I had the following thought. I was doing the other day I was reading a couple of papers and doing some back of the envelope calculations, and it seems that it's very likely that for the local universe, it should be able to find binary newtonian mergers that will be localized enough to be observed by wide field optical or medium field optical telescopes, and at the same time be able to detect ahead of time, an hour or even more, their merger, which means that you can turn your telescope there and wait for it to happen. And 1 hour is enough even to turn a satellite in some cases. What will we learn if this thing, what extra information will we have? What new thing we will learn if we manage to do that?
So you are totally right. So the one that I showed that have a good sky localization are exactly the one through which we can detect them pre-merger. For some of them is hours, for some of them is also minutes, but is already a pre-alert that is extremely important. From my point of view, okay, for high energy satellite, this is not extremely important because they are wide field of view. But for example, there is a very interesting part that is the very high energy. So for example, CTA. There you can really use this pre-alert to try to detect, for example, the prompt emission that was not detected so far in the very high energy, and then detect also the afterglow. That is what we are detecting now. And the volume up to which we can see both, we can have a good sky localization is exactly the same region where CTA can detect this type of emission. So for the very high energy, I think that this is crucial. Then it's clear also for the optical, you can start the observation and try to detect the early emission in optical. And also there, I think it's very important to understand the GRB, the first emission of GRB. So we are used to detect the gamma ray, but knowing if there is something related to the prompt in the optical phase is something that is very important to understand the GRB emission mechanism. For Kilonova, I think, okay, you can detect the first emission, so there is interesting. But for Kilonova, to me, it's really very important then to have a very good spectra to make nucleosynthesis. So there, I think that the best moment is to try to have the best spectra from the second, third day. That would be really the goal, the main goal.
Okay. Okay. Another question from Alexandra Olayak.
Hi, I just would like to ask, for how long, due to your predictions, Einstein telescope would work together with LIGO detectors? Because as far as I know, the time of the service of LIGO is limited for some near future.
So there are now groups that both in Virgo and in LIGO are trying to understand what are the possibility to use entirely the infrastructure to have upgrade of LIGO and Virgo. Clearly, up to the moment at which the third generation will be operative, LIGO and Virgo and CAGRA are expected to observe. In Europe, clearly, when at the moment in which ET will start to observe, the presence at least of Virgo will not have any scientific motivation that Virgo stay online, because Virgo is too close to Einstein telescope that cannot improve anything. But if it is alone, you can have improvement with the other antenna that are around. In the United States, there is also this, before Cosmic Explorer, there is also this other instrument that is, oh, now we have a moment without the name, that is, so it is something in between LIGO and Cosmic Explorer, and is again the maximum exploration, the maximum use of the LIGO infrastructure.
Okay, I'm sorry
Thank you.
Yeah, okay, thank you. One more short question. I see a question from Doga and Marika, if you could give possibly a short answer, because we will have to move on, okay?
Okay, so my question is about the detection prospects for supernovas or similar unmodeled searches. So you show a distribution for the sky localization and the distance for binary neutron stars, but is there such a thing for such burst emissions?
Okay, so for supernovae, we expect to detect supernovae with ET in the local universe, so we cannot go very distant. But to me, something that is promising, so this is taking into account the core collapse and the last simulation that indicate you an energy emitted in gravitational wave that is not very high. But something that I think is more promising than the core collapse itself is if you form a neutron star. So we expect that we don't know what is the rate of core collapse that produces a neutron star, but if you form a neutron star, you can have a signal that can last from hours to days, and this signal can be detected at least up to the Virgo cluster, but also up to, it depends a bit on the model, up to 50 megaparsec. So I think that it's more promising the post-collapse signal than the core collapse signal. But this is very interesting because then you can really relate it also to the electromagnetic emission, so also to shock breakout in the high energy and then the optical part. So I think it's more interesting, it's more promising this with respect to the core collapse itself. Okay,
Thanks.
Thank you very much. Thank you, Marika, for your talk and answering the questions. Let's move on to Alessandro Drago. Yes, we'll have a talk about Kilonovae from black hole neutron star mergers. Its next two talks will be on that subject, which is very important and timely given recent detections by LIGO.
Thanks a lot.
Alessandro, please.
Yeah, thanks a lot for this possibility of
Could you raise your volume?
Oh, let me try. Is better?
Better, thank you.
Better, okay. So these are essentially the main points that I want to touch. So the idea is we just used some parameterization of numerical simulations for estimating the amount of mass that is presumably ejected in a black hole neutron star merger, either forming a disk or dynamically ejected. And the point is that the amount of mass ejected is strictly related to the tidal deformability of a neutron star. And in terms, it is well known that the tidal deformability is also strictly related to the radius of the star. So now we have these new results from NICER, and these results from NICER are putting very interesting limits on the radius. And therefore, what we have done is, first of all, to compute the amount of mass that is emitted in the case of neutron star black hole merger in the normal scenario, where normal scenario I mean a scenario in which there is only one type of compass stars, only neutron stars, let's say. And we have compared the result of that scenario with another scenario that, of course, is very speculative, which is this two-family scenario in which neutron stars and strange quark stars can both exist. The interesting result is that there is a very big difference between what is expected in the normal scenario and in the two-family scenario. The main reason that I can anticipate is that in this two-family scenario, as I said, a scenario in which some of the stars are strange quark stars and other stars are neutron stars, but with very small radii, then what happens that there are already simulations indicating that quark star black hole does not produce any kilonova because all the material is immediately absorbed by the black hole. And second point, the other family, the neutron star black hole merger, also produces a very small amount of ejected material because the radius is very small. So I think that this will be, to study the kilonova signal associated with black hole neutron star merger will be a very good way to test if the normal scenario or the alternative scenario are correct. So let me start by this simple point. So as I said, and I'm going to show, NICER has measured radii, but actually there is a very simple and almost linear relation between, let's say, the radius of a 1.5 solar mass neutron star and the tidal deformability. Don't look at the lower part of the figure that is not really related to what I'm discussing here. So you see that this relation is simple and almost linear. So these are the results by NICER, and in particular, these two area here, the brown area and the dark red area, are the two independent analyses of this object. So they are indicating relatively large radii for an object having a mass of about 2 or 2.1 solar masses. The previous NICER result was this brown area that is less restrictive in a sense. And interesting also, there was another analysis made also by people of the group of NICER, by Miller et al., where they combined together the two analyses by NICER with what you can learn from GW 170817, of course, assuming that there is only one family of compass stars. So let's concentrate on this figure here, which is the result of this analysis. And as you can see, Miller et al. Are suggesting radii, as I said, relatively large, 12.4 kilometers. Okay, there are bars still there. And what we have done is to select 3 representative equations of state. These equations of state are 3. One is a mean field approximation, another non-relativistic, another is a relativistic equation of state, but it doesn't matter the detail. What matters is that, as you can see, they are essentially spanning almost all the region allowed by this analysis by Miller et al. So these 3 equations of state goes from almost the softest equation of state still acceptable according to Miller to the stiffer equation of state. The green line I'm going to discuss in a moment, and is instead what you get if you claim that strange core star can exist. As you can see already, strange core star can fulfill the limits of Miller. So, as I was mentioning, the amount of mass ejected is directly related to the tidal deformability. And you can see from here that the three equations of state that I was mentioning are occupying the upper part of this graph. So they have rather large tidal deformabilities. And for instance, this green equation of state is already a little bit excluded by the analysis of Miller. And moreover, what is interesting is that the equation of state that instead are inside the two family scenario are the equation of state which are extremely soft, and therefore they have small radii and small tidal deformability. So already from here, you can see that the group of equation of state which are satisfying the limits of Miller in the normal scenario are well decoupled by the equation of state that instead are interesting from the point of view of the two family scenario. So I was mentioning a few times this two family scenario, but I'm sure that most of the people are not aware of what it is. So let me just summarize very rapidly what it is. The idea is the following. The idea is that we can have neutron stars in which hadronic resonances and hyperons are produced. And because of that, then these hadronic stars can have very small radii, but they don't reach two solar masses. Okay, so we can fill this area here. Instead, which are the objects filling two solar masses? Strange core stars in this scheme. So as you can see, there is quite a big difference between the radii of objects of the first family, very small radii, respect to radii of objects of the second family, strange core stars. There are a lot of technical details, but I cannot enter because time is limited. Which are the justification of discussing such a scenario that is clearly speculative? Well, the justification are that after all, during the tens of years almost, there have been a lot of suggestions that objects having very small radii do exist. And some of these analyses are not really very old, 2018, 2019. Another interesting suggestion that maybe this two family scenario has to do with reality comes from the fact that there is an evidence of bimodality in the mass distributions of neutron star, a particular subclass millisecond pulsar with a white dwarf companion. It's funny because this bimodality is discussed in these papers is almost exactly sitting on top of what we would call first family objects that are really not reaching two solar masses, and second family strange core stars. And finally, let me mention a theoretical issue. The theoretical issue is it really easy to reach masses larger than two solar masses with neutrons, protons, resonances, and hyperons? Well, it is very difficult. For instance, this recent paper shows that it is perfectly possible to arrive at two solar masses if you don't switch off arbitrarily, so to say, the channels, for instance, concerning the hyperons. You see that this, for instance, this black line is very interesting because it satisfies very well the limit of Miller, but as the authors themselves have concluded, it is very difficult to reach masses significantly larger than two solar masses. This is a theoretical problem, but is a serious problem because it's not that we can neglect the possibility of forming resonances. They exist, and we have to deal with this problem. So I mentioned that in this scenario, what has been measured by NICER would correspond to a strange core star. And funny enough, we made, just before NICER result appeared, Bayesian analysis using other data, so not the data of NICER, and we were obtaining this curve with our strange core star. And as you can see, this limit of NICER are sitting perfectly fine with a strange core star. So let's now go to the question of the kilonova. So as I was mentioning, we are just using parametrization of the mass of the disk and of the mass dynamically ejected based on these papers. We are just completely borrowed from them this parametrization. And essentially, if you use this parametrization, what you have to provide is the tidal deformability and the compactness. So these are the results. So let's concentrate, for instance, to start with a 1.4 solar mass neutron star. And let's compare what happens in the one family scenario. This corresponds to an equation of state that passes almost exactly through the center of the limits obtained by Miller. So this is, to say, the most orthodox of the possible orthodox equations of state. Okay. So, and what these graphs are showing is essentially the amount of mass in the disk and the amount of mass dynamically ejected. Here is the legend. And now compare with what you get in the two family scenario. So in the two family scenario, let me just remind you this, the radii are much smaller. So the tidal deformabilities are much smaller. So it's certainly not a surprise that we are getting much smaller masses of the disk and significantly smaller dynamically ejected mass. It's even more clear in this second figure. Here instead we concentrated on a 5 solar mass black hole spinning at this 0.4. And again, you can compare, you recall that I was mentioning the NICER results are very well spanned by 3 equations of state. Let me just remind you this little detail. The 3 equations of state are these 3 equations of state, which are essentially covering completely the analysis of Miller, and is compared with an equation of state that instead is very soft and is representative of a two family scenario. And so these are the 3 curves that are satisfying the limit of Miller, or here. And this red curve is what you get in the two family scenario, because, let me tell again, the radius is very small. So as you see, there is a huge difference. For instance, if you take a neutron star having, I don't know, 1.3 solar masses, essentially you get 0 and 0 in the case of a two family scenario, and you get a finite amount of mass dynamically ejected, and in general, a finite amount of mass in the disk in the normal scenario. So let me conclude this talk. Maybe I've been even faster than expected, but anyway, telling essentially that there is apparently a very easy way to test the normal scenario compared to this two family scenario. It is to study kilonova signals in the case of neutron star black hole. And the reason is very simple. In the one family scenario, now we have a limits due to NICER, indicating relatively stiff equation of state, and therefore relatively large amount of mass ejected. Therefore, relatively large, really strong kilonova signal. In the case of the two families, the objects which are very massive and very stiff in a sense are strange core stars. But strange core stars, due to this analysis, simply cannot produce any kilonova when they merge with a black hole. So this is one of the reasons why we don't get a strong kilonova. The second reason is that since we want to have small radii for the first family, because the raison d'etre of this scenario is to eventually explain small radii if they exist, then again, also in that case, we don't get a strong kilonova. Let me just conclude this telling that, of course, this is not the only prediction of this two family scenario. We produced a lot of prediction. There is in a sense, even more striking prediction, which is related to neutron star mergers. And the prediction is if you have only one families of neutron stars, then since GW17 or A17 was not corresponding to a direct collapse to a black hole, then you don't expect to have a direct collapse to a black hole for any neutron star merger having a mass comparable or smaller than GW17, etc. In the case of the two family scenario, you do expect that, because in that scenario, I don't take time now to show why, but in that scenario, GW17, 0A17 was the merger of a neutron star and a strange quark star. And instead, if it was the merger of two neutron stars, it would have had a direct collapse to a black hole. So there are actually several very sharp predictions of that scenario. And so I hope that we can at least prove that we are wrong, so to say. Thanks a lot.
Thank you very much for the talk. Let's see if there are questions. I think Tassos is first.
Hi, thank you for the talk. As you were talking about the possibility of having strange quark stars and neutron stars at the same time, what I was thinking, since I'm coming from the stellar evolution point of view, is can you speculate what kind of stars would lead to the one versus the other?
Absolutely. Yeah, this is something that we spent many papers on. So essentially, the main discriminant is the central density. And what you expect is that for all the type of normal masses, I mean, normal are the masses that in the past were considered normal, 1.3, 1.4 solar masses. You just don't reach the critical densities at which you start producing so much strangeness in the form of hyperons that after the object this can reconfigure as a strange quark star. So that is why I had this figure here, indicating that the first object here are for us normal neutron stars. I mean, objects containing hadrons. Is explained in this figure here. In a sense, for instance, you have this first family. When you reach this mass, you collapse to a strange quark star. There is a little overlap here between the two families, exactly because it is an exothermic process. So the first discriminant is essentially that, is the mass. So object having a mass that does not exceed, let's say 1.5 solar masses, are most likely first family. Objects of 1.6, 1.7, 1.8 for us are, for instance, the object of 2 solar masses for us are by force strange quark stars. For instance, all the objects that you are producing in a merger of 2 neutron stars and which are not black hole, in this scheme are by force strange quark stars.
My question was more on pre-collapse stellar properties that would lead towards the formation of a neutron star or a strange quark star.
Yeah, that is also very interesting. I mean, what we can expect is that if you have progenitors having a normal mass, let's say a mass of the order of 10, 15 solar masses, the mechanism of supernova explosion is effective and it produces neutron stars having the standard mass. What you can expect is that when you increase the mass of a progenitor, it becomes very difficult to have supernova explosion in the normal scheme. So you can have an extra injection of energy because of the process of deconfinement between going from a neutron star to a strange quark star. The amount of energy released can largely exceed 10 to 53 ergs. So you have a fantastic peak in neutrinos at the moment in which you are deconfined. This is something that many years ago I discussed with Chris Pryor, if he's still around, probably recalls about that. And so the idea is that if you have progenitors which are very massive, under certain conditions, you don't have a normal supernova explosion that would fail. You start having fallback of mass. At that point, you reach the critical mass. The system deconfines. We have checked that the central part can deconfine in a few milliseconds. And therefore, you release this fantastic flux of neutrinos that can stop the collapse and make the supernova explode. I don't know if this is more similar to what you were asking.
Yeah, yeah. Thank you.
Very good. Any other questions? Anybody would like to add a comment? I don't see anything. I would have a short question just to reiterate what you said. So you said that you don't really expect any mass ejecta or kilonova with strange star and the black hole merger. So if you would see black hole neutron star gravitational waves and you would detect associated kilonova, then you would bet that it was a normal neutron star. Is that correct?
Yeah, I mean, if we see strong kilonova signals, it is very unlikely to accommodate this in these two families. Because so I think that I like the idea of having a test.
Yep, now fully clear. I appreciate that. Thank you so much for your talk. And we'll move on to another talk on black hole neutron star kilonovae, associated kilonovae, or lack of thereof, by Jinping Zhu. Jinping, please share your screen. I think you will be able to do this in a second. Yes, you can go to a full presentation mode. The floor is yours, please.
Thanks. Hello, everyone. I'm Jinping Zhu, a PhD student from Peking University. The title of my talk is No Detectable Kilonova Counterpart is Expected for all three neutron star black hole candidates. And here's our collaborators. Binary neutron star and neutron star black hole mergers have long been proposed as the progenitors of short gamma burst afterglow and kilonova emission. Very exciting observation at 2017 August 17th. LIGO and Virgo firstly detected binary neutron star mergers, and after about 1.7 seconds, Fermi telescope detected associated short duration gamma burst, and after about 11 hours, many telescopes find it an optical counterpart, and this counterpart was consistent with the prediction of kilonova emission. And then we observed the X-ray jet afterglow from radio to X-ray band. So this event confers the association of binary neutron star, short gamma burst, and kilonova emission, and let us entered GW lead meeting messenger error. So after this event, many astronomers wanted to find more kilonova emission, and also as yet not discovered neutron star black hole GW events and associated neutron star black hole kilonova. So a week ago, LIGO released the first detection of two confirmed neutron star black hole GW events, and also before these two events, there are two neutron star black hole candidates. This events is not sure whether it is the astrophysical origin, and for this event, the secondary component may be the heaviest observed neutron star, or maybe the lightest observed black hole. So for this four events, they have really low effective spin, and the luminosity distance are approximate to about 300 MPCs. We now convert the black hole neutron star mergers GW events. However, despite many astronomers use many survey times to find the follow-up observation. However, no EM counterpart has been confirmed. So we may ask why we didn't detect any neutron star black hole kilonova. So we try to answer this question in this talk. The first reason maybe the probability regions for this following ones are too wide. For these two comforting ones, you can see the probability regions were too wide compared to GW17 or A17, and for one of the powerful survey telescope at present, ZTF, they only covered a half of the GW probability region for these three ones, at most half of GW probability regions for these two ones. So this may be the first reason for we didn't detect no black hole neutron star kilonova because of too wide probability regions, and we want to know. And another reason maybe all three neutron star black hole kilonova were to find for present follow-up. So we firstly need to know the luminosity function of the neutron star black hole kilonova. Here it's the like of GW17 or A17, and it can hardly be explained by one component. At peak time, a blue component is needed, and at late time, red component is needed. So based on this model, we consider three components. Also, the neutron star black hole injector should not be astropic. You can see this numerical simulation. The opening angle of the dynamical injector should be smaller than 20 degrees, and also after the merger, most of the material would be around the black hole, and due to the high temperature of the disk initially, and there would be a blue component formed towards to the polar direction, and then due to for example, magnetic instability, there would be a purple component moved towards to the equatorial plane. So you can see the neutron star black hole kilonova should be anti-astropic. Here we show some an example. For neutron star black hole kilonova, most of the dynamical injector would contribute most of their emission. Compared with the GW17 or A17 at early time, neutron star black hole kilonova should be dimmer than the GW17 or A17, but at late time it could be brighter. Especially in infrared, could be brighter than GW17 or A17. And also we show some viewing angle. In fact, we define two viewing angle. One is the theta viewing angle here, and another is the phi viewing angle here. If we change the theta viewing angle, there would be the Leica would have much different. And this is because if we change the theta viewing angle, the projected photosphere area of the dynamical injector would have a larger change. and the difference between the maximal and the minimal peak luminosity is about 2 to 3 factor. In order to know the luminosity function, we need to know the dynamical, especially for the dynamical injector distribution, and this distribution is related to two radius. One is as zero radius, and another is tidal disruption radius. And the former one depends on the black hole mass and black hole spin, and the later one depends on the neutron star mass, neutron star increase of state, and the black hole mass. Here we assume the different neutron star mass, black hole mass distribution, and the spin distribution. And the spin here is the projected aligned spin of the black hole. You can see most of the emissions may be dimmer than minor 16th. So due to the time limit, I skipped the wing angle effect discussion. So if for O3 events, we know most of neutron star black hole mergers should their distance range should be in the range of 200 to 400 MPC, and this is similar to the observations. So if we assume the neutron star black hole kilonova have a peak magnitude of -16 magnitude, they could cover the most of this distance for O3. However, the time window could be really low for ZTF. So it's really hard for ZTF to detect the neutron star black hole kilonova in O3. So in the future, maybe 23 to 24 magnitude detection depth is required, so we can be more easily to find some neutron star black hole events. So because some neutron star may be directly plunged into the black hole, we now consider whether these four events could be plunging events or maybe disrupted events. Here we use three equation of state. One, this event may be one of the best constrained equation of state by GW17 or A17, and this equation of state is the stiffest equation of state allowed one of the stiffest equation of state allowed by GW17 or A17. And here is the black hole mass and the neutron star mass. If the black hole have a line spin equal to 0.9, so the black hole neutron star in this mass range can occultidal disruption, but if they have really low spin, only less massive black hole and less massive neutron star can occultidal disruption. So we can see for these three events, they have really low spin, low projected aligned spin, so they are really hard to make tidal disruption. And we can see for this event that their tidal, the most the tidal disruption probability should be smaller than 20%, and for this 2-in-1 conferred by LIGO reason hard to make tidal disruption. Yeah. And we also can predict the luminosity distribution for these two sources. And you can see at present, ZTF can hardly to observe them. Yeah. And also, we now have a better constrained increase inventories. So we, based on the population synthesis results, only these two modes can be suitable for these inventories, and for these two modes, they assume the efficient and or very efficient angular momentum transport of the massive stars, and also high kicks will change the spin direction for black hole. So they would be decrease the in fact the aligned spin of the black hole, and also this spin distributions can explain the this spin modes can explain the spin distributions of O1 and O2 binary black holes. So we combine this mode to discuss the
I think 3 minutes. Okay, 3 minutes.
Okay. And here's the 1 sigma and 2 sigma distribution for population synthesis results. You can see the spin of these three events are located in the 2 sigma of spin distribution. So we can see only in this region, neutron star black hole can make a tidal disruption, and the probability should be smaller than about 20%. And we can also practice the luminosity distribution. Maybe only really small fraction of a neutron star black hole can be detected by LSST in the future. And also, especially in EP and CE Euro, the potential short duration gamma bursts and afterglows are more probable EM counterparts for neutron star black hole GW events. And also we discuss other possible reasons because in reason some ZTF find a possible EM counterparts for binary black hole events, and also some binary neutron star mergers and neutron star black hole mergers are predicted to be embedded in the agentic. So we discussed the probable EM counterparts, and also the short gamma burst jet would be tracked and the jet would deposit the energy into the cocoon. So there would be two shock breakout. One is the cocoon shock breakout and the ejecta shock breakout, and also the kilonova cocoon cooling emission would be outshone by the agent disk emission. And here is the structure. So in the optical, these signals may be missed by the observation. So finally, in future, LIGO and Virgo can give a better constraint for GW probability region, and we have some new optical service. Maybe in the future we could observe some neutron star black hole Kilonova, and finally the conclusion. So maybe that's
okay.
all.
Okay, very good. I think we got the message. Let me first ask other people a question. I have a couple of comments. Anyone questions? It may seem pessimistic, but it is what it is. We apparently seem not to predict many kilonovae from those type of mergers. If any questions, please just unmute and speak. Okay, since waiting for a question, I will comment on things. I've done a similar study based on population synthesis results, based on best equations of states that we have, on mass ejecta and measuring, kilonova brightness. So you find it even more pessimistic than what you find. We find that only 1 to 10% of black hole neutron star mergers would have any ejecta, any, with a stress on 1%, not on 10%. That's one bad news. And the second bad news is that we find them even dimmer than you guys. We find them at a peak of magnitude of about 25 magnitude, apparent magnitude for all three. So this is rather unlikely that I think that even in 04 we'll have a black hole neutron star merger with electromagnetic counterpart. Although I hope to be wrong. Okay, any other comments or questions? If not, Jinping, thank you very much for your talk. And let's move to another subject. We'll have Doga Veske talking about now multi-messenger astronomy with neutrinos and gravitational waves.
Yes.
Floor is yours.
Yes, thanks. Yes, as Chris said, today's focus was to electromagnetic counterparts, but I'll be talking about the neutrino counterparts, specifically to high energy neutrino counterparts. We have been searching for joint gravitational wave and high energy neutrino emitting events with our pipeline called LAMA, which stands for Low Latency Algorithm for Multi-Messenger Astrophysics. And we have been doing the search with the gravitational wave detections of LIGO and Virgo detectors and candidate neutrinos of the IceCube detector. And first, I'll start by talking about the common sources of gravitational waves and high energy neutrinos. So as you may know, in order to have a gravitational wave emission, you need to have a change in quadrupole moment in your system, and binary orbiting systems are perfect examples for this. However, you can also have such an emission from non-symmetrical ejecta. And in order to have high energy neutrinos, you need to have an energetic flow of matter. For example, you can have those high energy neutrinos from the decay of photomesons created in the AGN jets or gamma ray bursts. And when you combine these two, you may have the most probable gravitational wave and high energy neutrino sources as binary neutron stars, binary neutron star black hole systems, or binary black hole systems that are in an accretion disk or that has an accretion disk around themselves. or you can have such emissions from core collapse supernova. And now I would like to talk a bit on the detectors that we use. First, I'll talk about the gravitational wave detectors network. So there are several gravitational wave detectors located on Earth, and they all have different sensitivities. There are 2 LIGO detectors in the US. There's the Virgo detector in Italy, the Geo 600 detector in Germany. There's the newly operational detector Kagrai in Japan, which became operational last year. And there's a planned installation of LIGO in India. And all of them have different sensitivities, and currently all the detections have come from the 2 LIGO detectors and the Virgo detector. And the advantage of having a gravitational wave detector network is, first of all, you can combine the signals from these detectors and you can increase your sensitivity for sensing gravitational wave signals. But moreover, when you have multiple detectors, you can use the time of arrival of the signals, and you can have a better localization of the event in the sky. And such localizations are very important for, especially for multi-messenger searches. If you have 3 or more detectors, you can ideally constrain the location to 2 points on the sky. If you have no noise, but if you have noise in your detections, those points generally become some spots on the sky, and sometimes the spots can even be large for telescopes to scan. So localization is very important for multi-messenger searches or follow-ups. And next, I'll talk a bit on the IceCube. So IceCube is a high-energy neutrino detector located at the geographical South Pole. It is composed of so-called digital optical modules, or basically cameras, which are dug into the ice, and they look for the Cherenkov radiation coming from the particles that are hit by or created by the neutrinos. And the interesting kind of particles or the events for us are the muon tracks, which have much better localization compared to other kind of events where you have a lot of particles scattered around. If you have, for the muon tracks, you can constrain or reconstruct the localization of the event to a much smaller area in the sky. And IceCube is has all sky sensitivity. It can sense all the particles coming all sky, but it has a higher sensitivity for the particles coming from the neutrinos coming from the north hemisphere, because Earth kind of behaves as a filter for atmospheric muons. For the southern hemisphere, you have a noise coming from the atmospheric muons, but for the neutrinos coming from the north or coming or the upgoing muons, you don't have such a noise. So it has a slightly better or significantly better sensitivity for the northern hemisphere. So let's get back to what we are doing. We are searching for joint gravitational wave and high energy neutrino events, and if such events happen, it will be a multi-messenger event, and we can learn more about the processes that happen before, during, and after the event, because such emissions may happen at different times. And moreover, with such multi-messenger detections, you can guide the astronomers in low latency with better localization. So gravitational wave sky map sizes can range between 10 to 10 thousandths of square degrees alone. And the high energy neutrino localizations are generally between 0.10 to 10 degrees square. So this is a significant improvement by itself, but when you consider their overlap in the sky, you can constrain the area that needs to be scanned by telescopes to a smaller region. And on the right, I show an example for this. So this was a candidate joint detection during our real-time follow-up for O3. Here, this orange gradient shows the probability distribution of the localization for the gravitational wave event, and this orange, the blue circle is the boundary of the 90% containment of IceCube neutrinos localization. And there was a search performed by Swiss satellite after we shared this neutrinos localization, and such low latency searches made such additional searches possible. So here, what's the problem that we are trying to attack or we are trying to solve? So we are searching for coincident neutrinos in a given time window around the gravitational wave event. For us, this is plus and minus 500 seconds. This number isn't very fixed, but it comes from the distribution of gamma ray burst precursors. And the candidate detection rate in this 1,000-second window, at least for IceCube, is around 6 or 7. So there is going to be some unrelated neutrinos or candidate neutrinos or neutrino triggers coinciding with the gravitational wave localization, just because of this detection rate. So then we are trying to answer these 3 questions. First, is this gravitational wave real? Second, which of these neutrinos look like astrophysical neutrinos? Because most of them are actually not astrophysical neutrinos, they are just noise or atmospheric muon tracks. And finally, the interesting question is, which of these neutrinos could come from the same source of the gravitational wave? And we are trying to have the lowest false negative rate at a constant false alarm rate, or in other terms, we are trying to miss the least amount of astrophysical neutrinos at a fixed significance. And we are developing new statistical methods to achieve this better. For our search that we used in O3, we improved the method that were used before by including the information on neutrino emission energies, which allowed us to use the distance reconstruction of the gravitational wave events. This is something that we do differently compared to the previous or other current searches. We use the distance reconstruction of the gravitational wave to have a better statistical power. And more recently, we actually extended this method and made it and developed a generic method for arbitrary number of multi-messenger detections, multi-messenger types or counts in a study that we published recently, where we actually showed that for such generic multi-messenger searches, there isn't a model independent optimal search. Any search you have has to favor some kind of model. And we showed if you assume a model, how can you do it with the highest statistical power? So going on to previous analysis that we did, so we did an offline search on the archival data on the GWTC1 events from O1 and O2. So GWTC1 had 10 binary black hole mergers and the binary neutron star merger from O1 and O2. And we looked for coincident neutrino counterparts to these events, and we didn't find any significant emission. The most significant event had a p-value around 16%, which is very consistent with being unrelated. And what we do more is, since the gravitational wave events come with their distance reconstruction, we can put upper limits on the neutrino emission energies rather than the neutrino fluences on Earth, because we have the distance reconstruction from the event, we can put a limit on the emission energy itself. And the lowest 90% upper limit belonged to the binary neutron star event, mainly because it was the closest event detected so far, and the upper limit was around 10 to the 51 ergs for neutrino emission. So now I'll move on to our real-time search that we did during O3. So as you may know, O3 was the third observing run of LIGO and Virgo detectors. It's supposed to be a 1 year long run, but it got suspended a month before its completion due to pandemic. And one thing that O3 had differently compared to its previous runs was LIGO and Virgo collaborations shared their candidate detections through a database in low latency, which allowed such additional real-time searches, which made our real-time search possible. So we performed the real-time search for each of these candidate detections, and we shared our results through GCN circulars with the community. There were a total of 56 non-retracted alerts, and we did analyze all of them. 3 of the events had a p-value less than 1%. This was a threshold value decided by the IceCube collaboration. And I should also mention that in IceCube collaboration, there is also another search that has a slightly different method, and we both analyze these events. Here I'll be talking about our search. So there were 3 events with p-value less than 1%. There were 2 of them were candidate binary black hole mergers, and 1 of them was a candidate binary neutron star merger event. And we shared the information of the coordinates of the neutrinos corresponding to these events, and those neutrinos triggered additional searches from different observatories, such as Salk Observatory or the Swift satellite. And on the right, I show a GCN circular for one of these events. This first one, S190728. So we shared the relative time difference between the detection times of neutrino and gravitational wave event, the coordinates of the neutrino, the angular uncertainty of its sky localization, and the p-values of the analyses. Now I would like to focus one of these 3 events, which I think is interesting. This event was from December 2019. It was a candidate binary black hole merger, and it was actually a rather close candidate binary black hole merger, about 400 megaparsecs away from us. And there was one significant neutrino coincident with it. And it was only significant for our search, and not that much significant for the other search. And the main difference between these 2 searches is the use of the distance information. And what made this event significant for us was the fact that it was a closed binary black hole merger. And on the right, I again show the overlay of the neutrinos localization and the gravitational waves localization, as well as the Swift satellites search tiles. This is again from the same publication. But what made this event interesting is after we sent out the neutrinos coordinates, Hawk Observatory replied with another GCN circular saying that they have a subthreshold gamma ray event that is coincident both with the gravitational wave localization and the neutrinos localization. And this was very exciting for everybody at that moment, but nobody could be sure if this was a true triple coincidence or not, because this triple coincidence had subthreshold events involved in it, the events that were not confirmed as certain events, and nobody had the statistical machinery to assess the significance of this triple coincidence events with subthreshold triggers. And actually, after this let me say, triple coincidence, we developed the method that I mentioned, which allows you to quantify the significance of any kind of multi-messenger detections. It could be it could have sub-threshold events with any kind of or any number of messengers, which was published recently in the Astrophysical Journal. This brings to my conclusion. So we are searching for common sources of gravitational waves and high energy neutrinos, and we are also developing statistical methods for having better performance. We don't have a decisive discovery yet, and at the same time, as we look for discoveries, we are also guiding astronomers with real-time follow-ups for more possibilities.
Thank you very much. Thank you for finishing before time, so we can keep up with the schedule. I have some questions or comments, but let's see, maybe some other people would like to ask a question. Anyone? Or maybe if people are deciding on a question. I have a question that I probably must have missed it on one of your initial slides, but what is the realistic estimate of the farthest distance from which you can detect neutrinos with IceCube?
Yeah, so I mean, what is different in neutrinos than, let me say, gravitational waves or magnetic emission is that they come in counts. So one neutrino comes, or actually, if a neutrino comes, generally it's only one, never two neutrinos come. And that is related to the propagation of the signals in the space. So what you try to detect in gravitational waves or electromagnetic signals is the signal energy. And if you have a farther source, you will have a fainter signal or fainter energy density, and that makes it makes harder to detect compared to the noise. But for neutrinos, if you have a far source, it could be that just no neutrino hits you. So
of course,
further, the neutrino count density decreases, but it never achieves to zero. So the theoretical, like,
yeah, there's no theoretical limit, but
infinite, there is no
realistically, let's say you have some models how many neutrinos you produce per merger. When you apply that to to the increasing distance, at some point you get pretty much close to zero. You get below 1 neutrino per merger. So what would be? I just want to get a feel. Is it like 1 gigaparsec, half a gigaparsec? Apparently, you're considering several hundreds of megaparsecs in your study.
Yes. So it depends on the total emission energy. For example, this is related to the upper limits that we find. For example, this binary neutron star merger was around was like 40 megaparsecs away from us, and the upper limit that IceCube says IceCube can put is at 10 to the 51 ergs. So if you have a higher emission energy, it could be possible to detect or realistic to detect neutrinos from that far away. And if you have like higher energies, you can detect from farther away. So it's related to the total emission energy.
Okay, fine. Let me try one more time. If I don't get the question, we'll go to Tassos. Just assume the most common emission mechanism, the most common energy, put it in a most common merger, any model, and try to give me a number if you can. If you don't know,
okay, yeah. So
give me the number. How far?
What I can give is, so I guess it's estimated, the emission energy is estimated to be similar with the GRB energies, and like the lowest one is actually from this binary neutron star merger, which is like 10 to the 46.
Okay.
I guess like the medium ones are like 10 to the 49 ergs. So if you divide this by 100, that makes like 0.4 megaparsecs.
0.4 megaparsecs?
Yes. So if
megaparsecs.
0.4 megaparsecs, so like 400 kiloparsecs.
Well, but you're considering mergers that are way, way beyond that limit.
Yes, yes. I mean,
so I'm missing something here.
So in that case, you would really expect to see something. Here, we are kind of trying to be lucky.
Okay, you're on a fishing expedition, but okay. Okay, but I got the number. Thank you so much. Tassos,
Okay,
please go ahead.
Just a quick related question, because I think I missed the number. Given the new, more updated statistical methodology that you talked about in one of your last slides, what is the chance of random triple coincidence for the binary black hole merger?
Do you mean if we assume that these triple messengers are emitted, what is our chance to detect them?
No, I'm talking about the specific binary black hole that coincided in time.
You mean, okay, this one.
Yes. So what is the chance of triple coincidence? I guess that's based on your updated.
Yeah, so we didn't analyze the triple coincidence of this, so we developed the method, but the analysis requires expertise of 3 of the detectors. So this was the gamma ray was detected by the Hawk Observatory. In order to assess this significance, you also need an expert of the Hawk Observatory to understand the behavior of the detector. So I don't have a number for
okay,
the
so
chance.
Let me pose the same question that Chris basically asked you. If you really don't expect to see a neutrino from that far away, what is even the
point?
How do you even calculate the triple coincidence chance?
So you can always calculate the chance of detecting a neutrino. So what Chris was asking was a realistic distance, and like I was mentioning this 90% upper limits from this far events. If you like plug in those emission energies, what you get is like 1 in 1,000 chance to detect for neutrinos. You can always detect, but yes, I have to say it's not so likely to detect. Otherwise, we would have detected, in my opinion.
Okay, thank you.
Okay, any other questions from anyone? No, if not, let's thank Doga again. And we'll move to the final talk of the session. This time it will be yet a different connection between gravitational waves. This time it's a connection to long GRBs. Tassos, please.
Thank you, Chris. So we have been talking for a while now about the connection of binary neutron star or perhaps black hole neutron star mergers and short gamma ray bursts. And what I wanted to talk about to you in the next 20 minutes is about a connection between binary black hole mergers and long gamma ray bursts this time. But the connection, in contrast to short gamma ray bursts and binary neutron star mergers, is not with the merger itself, but with the formation of the binary black hole. So what I want to talk to you about here is how we can probe the progenitors of spinning binary black holes with long gamma ray burst observations. And I should say up front that most of what I will be talking about has been done by the PhD student Simone Bavera, who is working with me, with a lot of contribution from a postdoc, Manu Zapartas, and a large number of collaborators that have contributed in the things that I will be talking. So let's start about binary black holes and how they are formed. I'm sure you have seen slides like this many times. So broadly, we can separate the different formation channels that have been proposed in the literature into 2 categories: isolated binary evolution and dynamical formation. with some overlap in between when we're talking about triple systems. What I will be focusing today is on the isolated binary evolution. And specifically, I will be talking about models that include 3 different subchannels: the common envelope channel, the stable mass transfer channel, and the chemically homogeneous evolution. So why do we, is it okay to focus on just this part of the parameter space, if you wish, or in this subgroup of formation channels? So using the recent gravitational wave transit catalog 2, there has been some work that was led by Mike Zevin and Simone Bavera, where what they try to do is to test some machinery that Mike has been building for a while, that aims at using the observation of gravitational waves in order to infer, on the one hand, the branching fraction among the different subchannels, and on the other hand, try to see if one can constrain some of the underlying model parameters. So this is mostly a showcase of what one can do, but at the same time, you get some interesting high-level results, which you should not take at face value, but it's interesting to start looking at some convergence that is coming out from different directions. So the interesting part with this analysis is that we try to put together a group of different formation channels, the 3 ones that I mentioned from isolated binary evolution, and also formation of binary black holes in globular clusters and nuclear clusters. And we tried to make the physics among the different models as consistent as possible. And what you do then is you take the predictions of all the models, you do a lot of Monte Carlo simulations, and you're trying to infer which is the model that contributes the most to the populations that we're observing. And now there are 2 answers here. There is the population that we see when we are looking at data coming from LIGO and Virgo. And there one finds that probably no specific formation channel can explain the formation of all systems. So what you get is that roughly half of the systems are coming from the fields from the observed ones, and the other half is coming from different types of dynamical formation. But then what you see with LIGO is not the true picture, is some distortion of the underlying population through the LIGO selection effects. And if you look at the underlying population, what you find is that actually the field population seem to be dominating or largely contributing to the underlying real intrinsic population of binary black hole mergers. Another thing that perhaps is even more strongly constrained is that there is a large preference that the birth spin of black holes is very small, and that points to efficient angular momentum. It points towards isolated single black holes being born with a very small spin. Similar conclusions have been reached by Franchiolini and collaborators here from the University of Geneva, but that's a coincidence, I guess, because I found out and we discussed about this paper with authors after actually it was written. But there are some other groups like the one from Wong and collaborators, which are finding slightly different results by using a smaller set of models. Now, let's see about the 3 events, the 3 channels that we're talking about here. The first 2, I will go very quickly, is the stable mass transfer and the common envelope. The evolution through this channel is pretty similar up to a certain point. The primary fills its rho slope, transfer mass to the secondary in a stable mass transfer. It strips its envelope. And because you have efficient angular momentum transport, as the star is expanding, all its angular momentum, it's transferred to the outer layers, which are removed. So the core that remains back after the star has expanded the giant phase and lost its envelope, is very slowly spinning. So it collapses to form a non-spinning black hole. Now the secondary star starts expanding, it fills its rho slope, and this second mass transfer phase can be either stable, in which case you collapse to form a black hole in a relatively wide binary, and you form the binary is too wide, so tides cannot spin up this helium core that will come to form the second born black hole. Or you have a common envelope which results in a closer binary, and in this case, tides can be strong enough that will tidally spin up this helium core, the black hole progenitor, and form a second born black hole that can be up to maximally spinning. Now, a third subchannel is when you start instead of a wide binary for a very close binary of two massive low metallicity stars. And there the tidal deformation from the rotation is inducing some rotational mixing. And what is that doing is bringing fresh hydrogen from the surface to the core, and you can burn the whole hydrogen of the whole star and basically fully mix your star and evolve chemically homogeneous. So these stars do not expand, but go from main sequence to helium stars, and they form directly two spinning black holes. All right, so stable mass transfer, relatively wide binaries, both of them non-spinning, common envelope, one non-spinning black hole, one spinning black hole, chemically homogeneous, two spinning black holes. Now, what we did here is we developed population synthesis models in order to follow the evolution of many, many binaries that go through these evolutions in order to get the statistical properties of the population. And we did this in a hybrid way, where we, on the right for these two channels, we evolved binaries using a rapid population synthesis code, in our case, cosmic, up to the formation of the first compact object, and then did the last phase of the evolution using detailed stellar evolution models. And we did that because what we cared is to have the profile of the rotational and density profile of the progenitor of the second born black hole, the one that might be rotating fast. And so we want to have a robust estimate of its spin. And in the case of chemically homogeneous, the whole the parameter is much smaller, so we could follow the evolution of the whole evolution using a detailed stellar evolution code. So we took all the simulations and we put them together using a new framework for binary population synthesis studies that, among other things, the main thing of this code is that it's going to use detailed stellar evolution to follow the whole evolution of the star. But in this case, we combined detailed and high and rapid population synthesis codes to get statistical predictions. And what that entails really is that you are using Monte Carlo, you draw initial binary properties from observationally inferred distributions, you evolve your population to form your synthetic population of binary black holes, and then you need to convolve that with the star formation rate and the metallicity of the evolution of the universe, and convolve the selection effects of the detector that you are using in order to make predictions about the detected population. And these three channels that I explained to you produce this two-dimensional probability density probability distribution. On the y-axis, I'm showing you the chirp mass, a combination of the two masses. On the x-axis, I'm showing you the chi effective. I guess all of you know about it. Is the mass-weighted average of the spin of the two black holes projected along the orbital angular momentum. And the two contours that I'm showing you here, I should say that the bright orange is 90 percentile, and the pale orange is 99.9. So this is really the whole parameter space that you can produce things, okay? And if I overplot, so what I should say is that on this part of the parameter space, it is mainly the chemically homogeneous evolution that is giving you binaries, massive black holes rapidly spinning. Black holes with low spins are produced by both the stable mass transfer and the common envelope evolution, while black holes that are relatively rapidly spinning but have low masses can be produced only by the common envelope. And in the observed population, we expect to see very few of them, right? But again, this is the observations. As I said, the underlying population can be very different. And I'm just overlapping here the events by GWTC2, where you can see that you roughly agree for the bulk of them, but there are several systems that fall completely outside our coverage of the parameter space. And this is a strong indication that at least these systems might be coming from another formation channel. But when we look at the underlying population, the picture is very different. Again, this is the 90th percentile and 99.9. And what you see is that there is a very large population of systems underlying that is not observable, where you have spinning black holes of relatively low masses. And the question is, how can we test, how can we probe this invisible, in a way, population of binary black holes? So this is where the long gamma ray bursts come in. And let's remind ourselves a little bit about what is one of the standard models for long gamma ray bursts, is the collapsar model. And in a graphical way, the way we should think about it, if this is the whole progenitor of the star that we imagine that it is rotating, then we can go cell by cell and identify, since we have the profiles of all of these collapsing stars, identify the part of its cell that has angular momentum larger than the angular momentum of the innermost stable circular orbit. And for the cells that this happens, this means that this mass here of this part of the cell will form a disk before falling onto the black hole, while material that is close to the pole and does not have enough angular momentum, it will fall directly. So having this profile of the star can give us a probe about how much will be the mass that will form a disk during the collapse of a black hole. Now, each one of these cells, as it is falling in on a dynamical time scale, it will form a disk. It will be accreted on a viscous time scale that generally is actually shorter than the dynamical time scale. The energy that will be released will form a disk with some efficiency, and it will be this jet, it will form a jet with some efficiency. It will be this jet that we're observing. And what we can measure is an isotropic equivalent energy of the long gamma ray burst, right? Now, in order to transform the mass disk prediction that we can make from our models to a prediction about the isotropic equivalent long gamma ray burst energy, there are two things that we should take into account. The first of them is this efficiency parameter that tells you what percentage of the accretion energy is transformed into a gamma ray jet energy. And the other is the beaming factor, because that tells you how likely it is to observe this jet face on, but also it collimates the energy and it makes it much brighter than it actually is. So how can you do that? We know the disk mass from our models, but what we also can do is we can go to observations and try to find an unbiased or as unbiased as possible sample of long gamma ray bursts. And in order to do that, we chose a soul survey, which is supposed to be complete for bright, for very luminous, very energetic long gamma ray bursts with energies above 10 to the 51. And we can see the energy distribution in red of this long gamma ray bursts. We can draw the distribution from our models of disk masses. and then combine these two factors into one and choose a value so that the peak of the two distributions is coinciding. And this is our way of calibrating our theoretical models to the observations. We are choosing this eta over beaming fraction to be about 0.2 so that the two distributions match with each other. And once we do that, then what we have actually achieved is we are now able to go in this part of the parameter space. This actual part of the parameter space is not two-dimensional. In reality, it is four-dimensional in terms of observables, right? So we're marginalizing over the other dimensions. And what we can get is at each part of the parameter space here, what is the chance, the probability that the binary black hole with this chirp mass and this chi effective was accompanied by a long gamma ray burst during the formation of the binary black hole. And I have chosen, sorry?
3 minutes, 3 minutes.
And I have chosen, thank you. And I have chosen from the GWTC2 the 10 events for which we are calculating a probability larger than 10% that they have been accompanied by a long gamma ray burst, and highlight 2 of them. These are the phone numbers for which we find a very high probability that the formation of this binary black hole was accompanied by a long gamma ray burst. 87 and 60% equivalent, right? Now we can go a step even further, and we can try to infer what is the rate of long gamma ray burst that one gets from the binary black hole merging populations. So what I'm showing here is rate density, and on with the gray band, star formation history density just for comparison. And these are binary black hole merger rate densities. This is with black, it's the total, and with orange, blue, and green, the 3 different subchannels. And of course, our models are calibrated. We have chosen a model parameter that agrees well with the rates and this distribution. So this is our best fit model overall. And then what can do is now, given the ratio that we fixed in the calibration, we have to make one more choice. We have to pick a beaming factor so that we can convert this into rates. And picking a beaming factor that is reasonable, 0.05, perhaps a little bit on the high side of the different values that have been suggested, we can calculate the rate density of long gamma ray bursts this time. This is the solid lines that is coming from each one of the models of luminous gamma ray bursts, because we're choosing only the ones that would correspond to a total energy of above 10 to the 51 Hertz. And since I'm giving the talk, I will also show here the observations that are coming from the Soul survey, and for which you can get that you are having a rough agreement with the rate that you are inferring during with our models of long gamma ray bursts. As I said, the exact rate is dependent on the choice of these 2 parameters. We can calibrate only the ratio, but then we need to choose values. So we cannot prove that the 2 are coinciding, but what we can find is that you can have a significant contribution coming from them that can be up to 100%. And I will put my conclusions here and take any questions you might have. Thank you, Chris.
Tassos, thank you very much for the talk and the connection between long GRBs and double black holes. Any questions to Tassos? I have, okay, there is one question from Alessandra.
Hi, very interesting talk. I would like to ask you about this stable mass transfer channel. And do you adapt any natal kicks for low mass black holes? And so, for example, the high eccentricity would help to merge them in the Hubble time, or is it just unconservative mass transfer? And also another one, what is the fraction of the black holes, for example, in terms of merger rates that comes from the stable mass transfer channel and the common envelope?
Okay, so three questions as I understood. The first one about kicks. So the kicks are fallback mass weighted kicks, the prescription that is described in the Star Trek papers by Chris. So we're not doing something special here. We're using the delayed prescription by Fryer. Now about the mass transfer efficiency, the mass accretion efficiency during the stable mass transfer. So in this phase here, we're assuming that it is Eddington limited, which shrinks more efficiently the black holes, the black hole progenitor compared to if you could accrete more mass. There you have a little bit of an interplay, right? If you allow for super Eddington accretion, then what that can do is that you can spin up this first-born black hole via accretion this time. This is not relevant for the GRBs, but you could have some black holes that have the primary black hole, the more massive spinning because of this reason. At the same time, you don't shrink this orbit as efficiently, and your rate is dropping. Somewhere in between, so changing at the same time the accretion efficiency, you can get to a point where you have enough to be observable with relatively large spins. And now about the rates that we're getting in these simulations, as you can see, is that locally we're dominated by the stable mass transfer. But as you go backwards in redshift, you're dominated by common envelope. Why is that? Because stable mass transfer has longer merger time scales. So the common envelope is tracing better closer to the star formation rate. But the exact weighting between the two depends a lot on the mass transfer stability criteria that you use. And since we're using cosmic here, the prescription is a little bit different than from Star Trek. And in fact, although we have tried to reproduce some Star Trek results, this is not possible with the machinery, like with the options that you have available, right? So the details of which one is dominating locally, I would say that depend on physics that is not fully understood yet. And I guess there some more detailed models can give us a better result. But again, SMT, you don't spin up the black holes via tide, so you don't get long gamma ray bursts.
Okay, thank you very much.
You're welcome.
Okay, I have a short comment on that. The rates that even at the local universe are so close to each other within factor of 2, and uncertainties are so high that it just close. Yeah. So I have a comment which I will follow with a question, not to get you, not to let you go off the hook that easily. That's a question about the first part of your talk and the branching ratios that are being calculated with Bayesian analysis by your group and by other people as well. So the thing is, and you are the one who really knows that the model uncertainties in stellar evolution and binary evolution are so big and are not included in most of the simulations that people are using for those branching ratios. How so? Do we really should we really be doing those studies at the moment, or should we rather be kind of forcing groups within each given model to assess all the uncertainties and build the models that encompass all those uncertainties, and only then to throw them together into the great statistical tool to get the meaningful answers? Because I think the answers right now are not really meaningful. Let's say all the binary evolution models that you showed do not include possibility that GW 1905-21 could have formed from single stars or binary stars. So the question to you is, do you actually believe those branching ratios, or you treat them as a kind of, okay? Well,
no. Let me tell you what I believe.
Yes, please go ahead.
What I believe is that if black holes were spinning, if single black holes were spinning fast, then you cannot get a good fit no matter which model you're using. So I trust this last part, that birth spins, which is kind of obvious, right? But it's good that it's coming out of this analysis. Before I go to whether I believe this, let me take a step back and say why I think it is important to pursue these studies, because it is important to slowly start building this machinery, testing it, understand the intricacies, so that when the data are here, we can actually do it. It is not as straightforward to interpret the results that are coming out of this. So I think that we learned a lot just by playing with the data, playing with the machinery without even looking at the data.
That part I agree with. I disagree with the part that you would just wait for more data. I think we actually need more work on model side to assess uncertainties, to put models that encompass all those uncertainties, because I think you can, with each model that you, well, not maybe with each, but you can pick one model, let's say homogeneous common envelope channel or non-conservative mass transfer channel, and probably can fit all those properties. If you apply tides in a different way, if you imply, mass transfer efficiencies in a different way, nobody has explored all those possibilities yet. So I'm talking, I think the limitation on models are driving those numbers more than the lack of data at the moment. Would you agree with such a statement?
Yes and no, but these go together. The more parameters, so here we were able to include 2 parameters. If you had 1,000 events, you would be able to do the same thing with 10 parameters to try to constrain. So data are useful to constrain physics. The more data you have, the better description you have of all the distributions, and you can discriminate between your models.
Okay, I get your point, but I still think more weight should be on the models. But fine, let's agree to disagree. And I fully understand what you're saying. So
we are in the same camp. Like I'm working on trying to understand the uncertainties, but we should all the time trying to discriminate also based on the data. And this is one way to do it. One important thing that came out of it, which is not discussed a lot in the literature, is the difference of what we infer for the field, for the detected population to the underlying, which can be stark.
That's a totally valid point. I agree here. Yeah.
So again, you can take it only from the point of methodology, that one should be careful when you say that 50% of the events that we see now with LIGO are coming from one channel because common envelope cannot explain it. When you go to the underlying population, this formation channel might contribute like a minuscule amount.
That's a valid point. I take it. Okay. Any other questions from anyone? Any comments on any talk? I guess it's getting late for everyone. So let me thank you all for the talks and all the questions and the discussions. And let me remind you that we'll be meeting again on Friday at 6:30 a.m. I know it's an ungodly hour, but we had to fit all the speakers across the globe. 6:30 a.m. on Friday morning, European time. And goodbye to everyone.
Thank you, Chris, for organizing this.
Goodbye.
Thanks, Chris.
Thank you. Bye.
Yeah. Thanks. Bye.